Let's start. Okay. Mr. Hegde has made a post there. I was just laughing at that. So, good afternoon, friends, and welcome to this second lecture, whose topic is geotechnical aspects of tall buildings. And we are, of course, this is the second lecture which IAS Shakti is organized for the towards disaster resilient earthquake chapter. That's the it's a 4-lecture series, and this is the second one, and it is being delivered by Professor Pradeep Kumar. Just by way of introduction, let me tell you a little about the lecture and about the speaker. Tall building construction is booming in the country, and besides the structural engineering aspects, there are several important geotechnical aspects which need to be understood and implemented from the planning stage itself. As a matter of fact, it is a matter of great concern that so much effort is put on the structure and not on the foundations and the substrata on which the loads are going to be transferred. The 1964 Niigata earthquake in Japan, the 1985 Mexico City earthquake, and 1995 Kobe earthquake again in Japan, and 2000 Bhuj earthquake are the notable ones where lack of understanding of geotechnical aspects is clearly visible. I will also show you an example. This is not only relevant to India or restricted to India. Even in the US, there have been problems which have been noticed, and I will show you at least one of them. The lecture focuses on geotechnical issues which a structural engineer needs to know. These are site-specific hazard assessment for tall buildings, liquefaction potential assessment, and soil structure interaction. Besides this, a structural engineer needs to understand the codal provisions pertaining to the above issues. In the recent edition of IS 1893, a simplified procedure for assessment of liquefaction and recommendations to perform soil structure interaction are included. About the speaker, you have already heard him in the first lecture of the series, but just in case there are some, and there would be new people who are joining this series of lectures, Professor Pradeep Kumar is an MTech from IIT Kanpur and a PhD from the University of Tokyo. His most notable contribution in recent times, to my mind, has been a primer on rapid visual screening of buildings for earthquake safety assessment, where normal people who are not earthquake engineering specialists can do an earthquake safety assessment of their buildings. Of course, he's a member of the earthquake engineering section of the committee of BIS and a fellow of the Indian Association of Structural Engineers. So this is briefly about Professor Pradeep Kumar, whom you have already heard in the last lecture, and I'm sure you're going to enjoy the one he has to present today on the geotechnical aspects relating to tall buildings. So as a precursor or as a preface to what Professor Pradeep Kumar is going to talk about, I wanted to show you what is the significance of the geotechnical aspects in tall buildings. So I have selected two buildings. The first one uh, being the what they are now calling the Leaning Tower of San Francisco. Let me just open my presentation. Are you able to see my screen?
Yes, sir. Clearly visible.
Okay. Yeah. So the Leaning Tower of San Francisco, I had mentioned, this is a 58-story building, and it is called the Millennium Tower in downtown San Francisco. As you know, that is one of the most expensive pieces of real estate in the world. And this building is the tallest residential building with over 400 multi-million dollar units. It comes in the top 10 most luxurious buildings in the world. Its cost was 350 million. And as you can imagine, the average cost, how much it would be. And the geotechnical issue is that this building, after having been constructed in 2009, settled 18 inches and tilted another 17 inches to the northwest. That is, towards one corner, it tilted. And the cost of engineering retrofit was fixed at $100 million. So that means about 1/3 of the total building cost, finished cost of the building. That was the cost of the engineering retrofit, which was given. So the comments from the public are, don't stand too close. Another one, not the big one, but just a moderate sized earthquake should be enough to increase the tilt to a point where the evacuation of the tenants can't be denied. So what exactly is apart from knowing that it is sunk and it is tilted to the northwest corner, and you can see the northwest corner, which has been highlighted in this square. The building, of course, is very tall, and it's, as you can see, the piles were terminated in what is called old black bay clay. So it was some kind of a strata, but most of the buildings in that region have also been have piles which are terminated in that area. As you know, for tall buildings, the thing that works is what we call the piled raft, which means that part of the load of the building, which may be several lakh tons. For example, this one I think was, if I remember correctly, some 800,000 tons is the weight of the building. So part of it is transferred by the mat foundation, and part of it by piles. So it's called the piled raft. And I'm sure that Professor Pradeep Kumar will tell you more about it. But this is what it was. And so the retrofit of $1 million, what $100 million they are talking about is that in this corner, they wanted to make more piles so that it doesn't tilt further. So this is another picture of the plan. As you can see what it is, they have extended the raft foundation, as you can see here, and they have made new piles which go down to the rock level. And to get that done, the structural scheme was that you push the pile down by the jack down method, which if you are a bridge engineer and if you've used well foundations, you know well, there are jacking rods which are fixed here, and then there is a beam, a structural steel beam, and we put hydraulic jacks here and push the whole thing down. So this is what the scheme is to push it, push this pile down into the rock level. So, but this scheme did not work. As of mid-August, and I'm talking, we are in the beginning of September. A few days ago, I would say, the foundation has sunk a full 1 inch, translating into a lean of 5 more inches at the top and a tilt of 22 inches. So it's uh, there is a further tilt while the work was going on. About, I think, half the work was done, and then suddenly this happened. And out of abundant caution, the the, the, the people who are in charge of the project, they say that we have taken a 2 to 4 week moratorium on pile installation while we try to understand better the mechanisms associated with increased settlement rate and available means of mitigating this. So many people are saying, is this the Pisa Tower of USA? Engineers are baffled as San Francisco's tallest luxury residential building keeps sinking and tilting. So the conclusion is that geotechnical issues, when they arise, are the most difficult to fix. As a matter of fact, structural engineering issues, when they arise, there are known solutions and we know what to do. But in the case of geotechnical issues, when they arise, it's very, very difficult to predict what is to be done. And even when you think that you've got the solution and you start applying it, it may backfire, as it has done in the case of San Francisco. So, just another idea which I want to give you, the amount of uh, uh, the amount of effort that people are making in the case of towers, case of foundations for tall towers. I have just taken 2 buildings, the Jeddah Tower, which is the world's tallest, and it is going to reach 1 kilometer high, and of course, the famous, well-known Burj Khalifa Tower at 828 meters. So in this, there are more than, you can see, 160 floors and 168 floors. Both the buildings, surprisingly, have the same kind of configuration, a Y configuration, which you can see on the left-hand side. And the piles, of course, go to different depths depending on the load distribution. Just to give you an idea, in the case of the Kingdom Tower in Jeddah, the raft, which is 4.5 meters thick, carries about 30% of the load, and piles, which are 1.5 meter and 1.8 meter, distributed all over the place, they carry about 70% of the load. And the investigations were done as deep as 200 meters to make sure that we don't get any surprises, because they know that this can't, if anything happens to the foundations, it can't be fixed. This is what it looks like, the Y-shaped tower, and it is a new type of structural system which is called buttressed core system. Nobody could imagine a few years ago that you can make a world record tall building in concrete. Everything is in steel. But in this case, they have proved that with some type of configuration, you can reach very tall buildings. And like I said, both these 2 buildings have a similar kind of configuration. Okay, so with this, I think, introduction, I would now like uh, Professor Pradeep Kumar to take over and start his presentation.
Thank you, sir. Thank you. That was really a wonderful precursor to the lecture. And
I
I'm
hope
going
that
to.
people have got sufficiently frightened.
Yes, yeah. Yes, yes. Yeah. So let me share my screen. 1 second. Can you see my screen?
Yes.
Yeah. So the title of my lecture is Geotechnical Aspects of RC Tall Buildings. So actually, I am not going to discuss about the geotechnical design of foundations, but actually what structural engineer needs to know, because that is expert is geotechnical engineer, and geotechnical engineer has to give expert advice. And but what to ask is also important. So that's why I'm pitching this lecture as a structural engineer perspective. So yeah, tall buildings in the world, and then this slide speaks about tall buildings in the country. Now, what I'm going to talk today is again for the people who joined in this lecture. So about brief introduction to the risk, and then what is earthquake hazard vis-a-vis tall buildings, and then we are going to understand our study site-specific hazard assessment and liquefaction potential assessment, soil structure interaction analysis. So three major items and one minor item which 1893 is giving, that is increase in bearing pressure. So how much increase is allowed, how much bearing pressure is allowed to increase. Now the risk, we know risk consists of the important factors or parameters in it, that is hazard, vulnerability and exposure. So these three things put together constitute earthquake risk. So hazard is the extent of ground shaking which building is going to experience, that is hazard, and exposure is the total area or total number of people who are exposed to such kind of hazard, and vulnerability is the capacity of the structure or how much structure can withstand to that level of ground shaking. So all these three things put together is risk. So hazard is not in our hands, it is in the hands of nature, and exposure is in a way controlled by municipalities, town planning, and then vulnerability, yes, this is where we come into picture. Architects and engineers control this one, or we can do something in vulnerability. So controllable parameters are these two, exposure and vulnerability. Now let me straight away go into the first topic, major item, that is tall buildings and what is site specific hazard. So let me give you a brief background of hazard assessment. So what is hazard? So it is a process of evaluating the design parameters of ground motion, earthquake ground motion. And what are the design parameters? One is amplitude of ground motion, duration of strong ground motion shaking, and the frequency content present in the ground shaking. So which type of buildings are going to get affected? Say low-rise buildings, mid-rise buildings, high-rise buildings, like that. So that can be understood. And then how we do, there are two frameworks. One is deterministic framework and second is probabilistic framework. Two are available. And then why we need to do? So we need to do to understand the behavior of buildings when subjected to such kind of ground motion. So we need to understand this one, especially for tall buildings. Now, say seismic hazard assessment, in this one, there are like these two things. One is a probability and second one is design life. And third item is the recurrence of earthquake. So estimating the probability with which a prescribed level of ground shaking, say 0.1 G, that means 10% of acceleration due to gravity is exceeded in the design life of structure. So generally life of structure is 50 years. So ordinary buildings, if we take 50 years. And the second way is like estimating the PGA, P ground acceleration, which is exceeded with prescribed probability, say 10% in the design life of structure. So now if you look at our hazard map, it has it does not address the question of how often shaking takes place of a given intensity. So area A may experience, say area A, let us take say intensity 8 in 50 years, area B in 200 years. So area A is say in say foothills of Himalayas, area B maybe in the like deep down, maybe in south. So 50 years is the return period of that, and 200 years is the return period of another earthquake. But 1893 puts them in both these earthquakes in the same zone, or both these areas under the same hazard level. So that is the point of concern. So we need to address. So now there are three kinds of hazards. One is macro hazard, which is generally used for normal buildings to understand the level of confidence and examine the adequacy. So this is done over a very, very coarser grid, that is 100 kilometers to 300 kilometers. That is the range of macro seismic hazard, and our 1893 code gives that. Then there is the second one, which is used for land use planning, risk assessment, that is microzonation. So this is done in the range of grid lines of 0.5 to 1 kilometer range. So this is micro hazard, micro seismic zonation also you can call it as. Now, what is more important for tall buildings especially is site-specific hazard assessment. Macro hazard will not give us a relief, or will not give us a proper data, proper information about earthquake, or what kind of hazard or earthquake shaking is going to occur. And then second is microzonation also will not give. So what we need is site-specific hazard assessment. So that is in the range exactly we need at the project site. So 1 meter up to 100 meters, that project site area. So how it is done? So broadly, what are the things involved in that? So as a step one, we need to find, say, sources. That means what are the sources which are potential of, which have potential of generating earthquake. So let's look at, say, site. This is site. And then we identify all the potential sources on which earthquake might occur, and that might affect our structures at site. So line sources, area source, all these things. So these things we can get from the map, which is given by Geological Survey of India. So fault map or fault database. So usually from the site, we go around 300 kilometers. That is the first step. And second step, what we do is find out the seismicity of that area, which is arising due to all these faults, all the sources. So number of earthquakes occurred in the past. So 200 years, 300 years, whatever number. So we get that magnitude and the frequency, magnitude class and frequency. So some magnitudes are like bunched into one category, like this one. You can see in the table, say 4 magnitude class, that means 3.75 to 4.25 magnitude earthquakes will be clubbed in that. So first event of that occurred in, say, this is hypothetical data I created. So first event in 1836 and latest event in 2020. So total number of events, 187 events occurred. So 4.5 magnitude class, 5 magnitude, like that up to 7.5, maybe 8 magnitude earthquake has not occurred in that vicinity of 300 kilometers from that site area. So this is called seismicity of the area. Then next one, the third step, what we do is recurrence. So we use this law, that is Gutenberg-Richter relationship, very famous law. So where we plot all those things in the graph and find out number of earthquakes more than magnitude M, whatever magnitude. So this is given by relationship A minus BM. So we get this one. Then next, fourth step, we find out the attenuation relationship. So the attenuation relationship means what? So at source, earthquake is occurring. At site, what will be the acceleration experienced? Okay, what will be the acceleration experience? So there are many attenuation relationships are available. So one such attenuation relationship I am trying to show you. So peak ground acceleration, as we move away from that area source, so peak PGA reduces, but together with the site condition, sometimes amplification also takes place. That I will explain that slightly later. So the mathematical equation to estimate the earthquake shaking. So that is felt at a site for a certain magnitude of earthquake. So this is a typical attenuation relationship. Here Y is the acceleration experienced at the site, and all the parameters are there. So what they mean, M is magnitude, R is epicentral distance, H, all the parameters we plug in to get the peak ground acceleration. Then next step is, now we come to hazard levels. So there are different hazard levels actually. So serviceability earthquake is one, design basis earthquake is one, maximum earthquake is another one, and then maximum credible earthquake is another one. So all these things are linked in one equation, which is P is equal to 1 minus e to the power of gamma t. So what is P? P is probability of occurrence of that earthquake, one earthquake, and T is the design life of structure, and gamma, that is 1 by R, where R is the return period of occurrence of that earthquake. So if I plug in those values and check serviceability earthquake, design based earthquake, so we can get this one. So serviceability earthquake means probability of occurrence is 50% and recurrence interval is 75 years. Design basis earthquake, this is what we use in our code, that is 10% probability of occurrence in 50 years. So that means 475 years is a return period. Then for important structures, we go for 5% probability and furthermore 2% probability. So that means what, if design basis earthquake, whatever PGA is there, if we understand the factor, we get say maximum credible earthquake 2, double. That means MCE, if we understand, divided by 2, that's how we got Z by 2 value. Z is for maximum MCE and Z by 2 is for design basis earthquake. So this is how we decide hazard levels. So depending on the project which we are envisaging at the site B. So now this peak ground acceleration we have evaluated at the bedrock level. Actually, it is at the engineering bedrock level. So what we got A max from that earlier equation, that is log y, is A max value. So that is, we know this probability of accidents and acceleration versus acceleration. So 10% probability, we were involved in one project of like vulnerability assessment of port structures. So there, this map we generated, that is 10% probability of accidents in 15 years, and this is 2% probability of accidents in 50 years. Now, what is the difference between these two maps? You can clearly see there is a difference. So if 2% probability of accidents in 50 years means PGA values will be higher, because we are looking for only 2% probability of accidents. PGA value will be higher. So depending on the type of structures we are planning in that site, this probability is decided. Then coming to PGA amplification. So whatever is founded, it is at the bedrock. Now we have to bring that ground motion as well as a spectrum to the site. So now for that there are several methods. I'm not going into those details. So shear wave propagation to the ground. So 2D and 3D methods are available. So this is one borehole data. So BH7 at Jangi. So you can see that borehole data is from ground to 45 meters, and different whatever is the soil condition is given there. Now this is the motion, which is ground motion, which is developed at the base rock, and then spectrum which is generated at that base rock level. Now, if we are bringing that ground motion onto the surface, depending on the soil condition, amplification is decided. So here it is very light amplification is there, not very much. You can see that. So PGA variation across depth. Sometimes what happens is when loose soils are there, amplification can go up to 3 times, 4 times also. So if acceleration at the bedrock is at say 0.1 g, when it is coming to the surface, it can be 0.3 g or 0.4 g even. So in summary, what is the site-specific hazard assessment? First is the source identification. Second is attenuation relationship. Third is PGA at bedrock level. And fourth is the scaling of ground motion, that is using amplification. And then PGA at the surface. So in summary, this picture is given. In this picture, we can clearly see the summary of that. And then finally, we get say PGA at the base and PGA at the bedrock level. So acceleration at the bedrock level and PGA at the ground level. And that one will be used for that should be used for like what do you call lateral load, used as a lateral load for finding out the induced earthquake force on that building, on tall building. So this is one. Now let's look at what are the characteristics of ground motion which will influence a tall building, vis-a-vis tall building. Now there are 3 basic characteristics. One is amplitude of the acceleration, or the displacement or velocity, and duration of shaking, and frequency content. Now these things we discuss. These parameters are influenced by other 3 parameters, that is magnitude of the earthquake, faulting mechanism or source, and then that is faulting mechanism, and second is path, third is site. So source, path, and site, these three things influence three earthquake ground motion parameters. Now let's look at, say, path, because which is important for tall buildings. So in path, when we see earthquake which is occurring very near to our tall building and very far away from the tall building, so it's called near field effects and far field effects. So what is the difference between these two? So let's look at this. Now in near field and far field, first thing is, when earthquake is in near field, ground motion will be impulse type ground motion, And if it is far field earthquake ground motion, then the motion will be cyclic type motion. Then in near field, so higher velocity pulses we can see, very high. And then when it goes, because earthquake energy will be very high, and in far field it is reduced. Then in near field, we see second order effect, like plastic buckling, that kind of thing. And then in far field, you see global mechanism. So these are the differences. So we need to understand our building is affected by near field earthquakes or far field earthquakes more. So this is one more thing. Then now code IS 1893 is giving some freedom to increase the soil bearing pressure under different conditions. So under what conditions it is giving, let us look at that in detail. So what it says is, so for design of foundations, we use unfactored loads in the load combinations. And whatever earthquake forces are there, so net bearing pressure in soils can be increased depending on the type of soil, depending on type of soil. So there are like three types of soil. Actually here, like what I would like to recommend is 1893 is giving for increasing bearing pressure, one soil classification. For reading the design spectrum, another soil classification. It is better to put both in one only. Two types are there, but it is better to put both as one table. A single table will be sufficient. Anyway, coming back to this one, what it says is, if the soil type is hard soil or rock, we can go up to 50% increase. 50% increase. But allowable bearing pressure can be enhanced up to 50%. Medium soil and stiff clays, we can increase up to 25%. And soft soils, 0. 3, and the fourth one is liquefiable soils that should not be used actually. So allowable bearing pressure, it already has enough factor of safety. That's why this percentage increase is given. That now for determining which soil type, okay, what code is giving is there are 4 soil types. How to decide? Well graded gravel, well graded sand, all that. But in bottom line is we depend on this SPT value. So N value above 30 means hard soil or rock. N value between 10 to 30 is medium soil or stiff medium or stiff soil, and N value less than 10 is soft soil. Now this loads, like 1 second, yeah, so 50%. So net bearing pressure, this N values, how to decide N values? First we test uncorrected N values, and then we do bearing pressure correction, that is Cn in multiply by N, uncorrected N values, we get the corrected N values. And code is giving what are the limitations of this corrected N values. So N values in zone 2, zone 3, zone 4 and zone 5. So at different depths, code is giving, 1893 is giving that values cannot be lesser than this one. That means certain types of soils are not acceptable. If the lower than that N values we encounter, then we need to improve that soil condition first before going ahead for the design of structures. So in zone 3, zone 4 and zone 5, less than 5 meters, 15 is the limit, and more than 10 meters depth, 25 is the limit. If we get 20 N value, more than 10 meter depth, then we have to do for soil stabilization and then go for the design of foundation. Okay. So you can see. Yeah, and then how the N values have to be computed, weighted average of different layers, weighted average. And say for different types of foundation type, how much depth we have to go, that details are also given in the code. I'm not going to that detail. Now coming to another aspect, which I feel this is very important for structural engineering to understand. So soil liquefaction. So some basics I would like to discuss first. So it's a quicksand condition, very well known phenomenon, where upward flow of water through sand under hydraulic gradient in excessive of unity, that is excessive of one, more than one. Then this is a phenomenon of saturated. This phenomenon is reported in many number of earthquakes. That is famous one, Bihar Nepal border earthquakes, and then Alaska earthquake, Niigata earthquake, Kobe earthquake, Bhuj earthquake. So this has been reported. So some glimpses you can see. Niigata earthquake, very famous like damage picture, and then like Kobe earthquake also we can see. So many pictures are available. Now coming to what code is saying about this liquefaction. So it is primarily in saturated cohesionless soils this occurs. Okay. Then when this condition is met, soil tends to behave like fluid mass. So this is now how the zone of liquefaction can be understood. First with the diagram, and then we'll go with the numericals, like numbers. So overburden pressure is always, say, at the zero depth, we have the depth of the building itself or depth of the foundation itself. And as we go down, then we, like overburden pressure gets added, it will increase. And then there is pore water pressure. On the surface, it is zero. And as we go down, it increases. So these are two known things. But the point is, when these two curves intersect, that is a zone of liquefaction. Okay. So in picture, we can understand this clearly. Now let us look at what are the parameters which are influencing this one: soil properties, environmental factors, and earthquake characteristics. These are three things. In soil, many things are there. Okay, so we can like study standard materials available on this: dynamic shear modulus. It's not static shear modulus, dynamic shear modulus. Damping characteristics, unit weight, soil type, grain characteristics, then density, then environmental factors, and then again earthquake characteristics, intensity, duration, and frequency content. These are the parameters which are influencing one single thing. Liquefaction potential of the site is influenced by all these things. So many parameters we need to take into account. Now, how to measure, how to reduce the liquefaction potential? There are so many techniques: adequate drainage, surcharge, piles, compaction. All these things are there. Some some methods of this is seepage. So using adequate drainage. So this is stone. This is exaggerated figure actually. So stone columns are drilled, and then we will allow excessive pore water pressure to get released. So in diagram we can see it like that, like this. So if we release excessive pore water pressure, the curve suddenly drops down. Thereby, these two are not intersecting. Overburden pressure curve and excessive pore water pressure curve, these two are not intersecting. So that means we are free from liquefaction. Then second one is what? Surcharge. You put a lot of weight, surcharge weight, and increase the overburden pressure line so that they are not, these two curves are not intersecting. So this is one way to get rid of liquefaction. So these are the two things, and then the combination of these two things. Now coming to how we assess the liquefaction potential of the site by knowing the parameters from the site. So this is what is given in IS 1893. Step-by-step procedure is given in IS 1893, which I am going to explain with some example also. So factor of safety against initial liquefaction. Simple. So CRR by CSR. Resistance ratio by stress ratio. Resistance ratio by stress ratio. Resistance is capacity and stress is demand. So capacity, demand. Capacity should be more than demand. So that means what? If this factor of safety is more than 1, we are safe. If this factor of safety is less than 1, we are unsafe. That means what? Soil will liquefy. Let's look at the procedure given in code. So step 1. So what we need to do is subsurface data. So get the data. What kind of data we want? Number 1 is location of water table, where it is, and then SPT blow count at different layers in the soil strata, and then mean grain size, then unit weight, then fines content. These are the parameters which we need to get from the geotechnical explorations investigation. Second one is we need to evaluate the total vertical stress and effective vertical stress. total vertical stress and effective vertical stress of all the potentially liquefiable layers in the deposit. So that means what, maybe from say surface up to say 10 meters, 20 meters, 30 meters, depending on the depth. Then evaluate the stress reduction factor. So at different depths, this is the stress reduction factor is there. As we go down, so reduction factor is applied. So on the surface it is 1. When we go down, so greater than 30 meters, it is 0.5 is the reduction factor. But code is giving one formula, this formula, how to reduce this one. So Z less than or equal to 9.15, some value is there. From 9.5 to 23, another value is there. If we, like, this procedure is actually adopted from Steed and Idri's work. So from 23 onwards up to 30 also there is another equation, and below 30 is 0.5 fixed value. So then step 4, we calculate the critical stress ratio. Okay. So how we do, this is the formula. This formula is adopted from Steed and Idri's formulation. That is A max is the acceleration, sigma V is the vertical overburden pressure, sigma V dash is the effective vertical overburden pressure, A max is PGA. If PGA, that is site specific ground motion analysis, for tall building, we need to go for it. For other structures, simply we can replace this that factor A max by Z as zone factor directly. And then G is acceleration due to gravity. And RD is the stress reduction factor, which we have discussed in step number 3. Then now critical resistance ratio, this formula, actually CRR value is given for 7.5 magnitude. So, but if other magnitude earthquakes might occur, if they may occur, what is the liquefaction potential of the site? So their magnitude scaling factor is given, and then this overburden, this like coefficients K alpha and K sigma are given. So K alpha usually is used for the sloping sites, and K sigma is the it depends on the overburden. So this is magnitude scaling factor. So 10 raised to the power 2.24 divided by MW power 2.56. So if magnitude is other than 7.5, the scaling factor is used. So this is K sigma. So correction for higher overburden pressure. Some details are there, how to plug in that F value. And then we get this K alpha, K sigma, and plug in to this one, plug in this one, magnitude scaling factor, and then we get CRR. So now, how to get this CRR? That is critical resistance ratio. There are, code is suggesting 3 ways of doing it. So either you using SPT blow count, or tip resistance in cone penetration test, or using shear wave velocity. So let me give this one. Actual formulation is this one. CRR is equal to some big equation is there, but with single parameter, that is N1 60 CS. So some details are given in that, how to get this N1, but finally uncorrected N values, then corrected N values, then overburden pressure correction, and then finally you will get this CRR value, CRR 7.5 value, and then you calculate CSR, the ratio. So now for one side, I will show you that this is CPT values procedure, and then shear wave velocity procedure. Now the final step 7, we will find out factor of safety against liquefaction, that is CRR divided by CSR. So if it is more than 1, then it is safe against liquefaction. But what code is suggesting is 20% higher. That means it should be greater than 1.2. It is not suggesting greater than 1.2. Then we can be assured that our site is safe from the liquefaction. Site means what? Any layer, every layer we have to calculate. Every layer we have to calculate this one. One example, you can see magnitude 7.7 is envisaged in that area. That means potential earthquake which might occur in that area, magnitude 7.7, and peak ground acceleration 3.36. And the other data of the site. So these are the layers. We are computing this at the 30 meter depth. So depth considered 30 meters, water table at 6 meters depth, fines content is there, SPT blow count, vertical overburden pressure computed is 1005 kilonewton per meter square, and then gross vertical stress, then stress reduction factor, because it is 30 meters, it is directly 0.5, and then CSR, okay, critical stress ratio is computed to be using this formula 0.182, and then CRR 0.061 using the expression given below, Now, if you do this factor of safety against liquefaction, we are getting 0.33. That means it will liquefy. If magnitude 7.7 earthquake occurs with PGA 0.3, actually PGA is important. Okay, so PGA, then this site will liquefy. Now, what I have done was picked in these numbers, changed the earthquake, and if we see whether for lower magnitude earthquake, whether this site will liquefy. So what I have done was changed magnitude to 6, and then peak ground acceleration is 0.24, just near to zone, like in zone 4 area. So even then it is liquefying 0.94. Further, I have reduced it. That is, magnitude is 6 only, but zone like peak ground acceleration is 0.16. Now it is safe in liquefaction, against liquefaction. So it has come 0.14. So this, what I have done was zone 5, zone 4, and zone 3. So the same site, if it is zone 5, zone 4, and zone 3. So what is happening is similar conditions, but zone 5 it is liquefying, zone 4 it is liquefying, zone 3 it is not liquefying. So people in higher zones, when we are planning for tall buildings, or for that matter, any building in soft soils, or like soils which are susceptible for liquefaction, let us not take it lightly. This is like what a structural engineering need to know. I'm not saying that we start doing this work now. It is geotechnical engineers will do, they are experts in that, but if we know, it is very good. Then, yeah. So then coming to soil structure interaction. Soil structure in tall buildings versus soil structure interaction. So soil structure interaction, the word itself is the term soil structure interaction. So what is happening is the process in which soil, that is motion of the soil, influences the motion of the structure. Now if structure moves, again it has to, that motion, that it has to be taken by soil itself. So motion of the structure influences motion of the soil. So these two. So there are two kinds of interactions. First one is called kinematic interaction. Second one is called inertial interaction. When there are no structures, if you measure the ground motion, that is called free field ground motion. So generally free field ground motions, if we use in structural design, they're not very much valid actually. We need to know what is the ground motion experienced at our site. So for that, we need to understand this one, soil structure interaction. Now, when it is important, now two codes, like one is 1893, second one is tall building code. Tall building code says that if height of the structure is greater than 150 meters, that means 30 floors and above, we have to go for soil structure interaction. We have to understand like how the foundation is influencing the response of the structure. Soil is influencing the response of the structure. Then the second one is 1893 is saying that not required for the structures founded on rock, hard soil at shallow depths. That means what? For all other structures, it is indirectly telling go for soil structure interaction. So in a way, so I put one table here when soil structure interaction is important, when a structural engineer should take it seriously. So high-rise buildings, yes. Low-rise, mid-rise, we need not take. High-rise building founded on rock, founded on medium soil, founded on soft soil. We need to take soil structure interaction into account. Mid-rise buildings, medium soil and soft soil. Low-rise buildings need not be considered. It's not recommended. I'm not saying need not be considered, not recommended. Then challenges involved for different types of structures, and after that I'll go to tall buildings. So first one is type A structure. This type A, this categories I'm putting a rigid tower, say like this, tower like this, right? So what happens is in this one, supporting soil media under ground shaking, that will go into non-linearity. Usually tower will remain in linear state. So directly that will fall down because of this soil structure interaction issue. Then second type, that is pile supported jetties. If we look at them, pile supported jetties, pile and soil both will be in under non-linear state, but jetty, that is main structure will remain in linear state only. It will not go into non-linear state. When it comes to structure, RC frame structure, that means whatever like structural system is there, say maybe shear walls are also present. You can see this one. So pile, soil, as well as structure, all will go into nonlinear state under strong seismic shaking. This is type C structure. And there is another category, type 4 structure, that is pipelines. Okay, long pipelines which are going across the fault line, crossing the fault lines. So in this one, supporting soil media will go to nonlinear state under differential settlement and pipe. Differential settlement and pipe will also go into nonlinear state. So all these things. But our focus is on buildings right now. Let me go there. Now let's look at this figure very carefully. Here, the structure is there and the black dot you observe. Because of the ground motion, this black dot, this entire ground is moved from here to here. So the first UG is the motion of the ground. And now relative to this dot, this foundation is, the structure is directly below the dot. Now you can see the structure has moved from the dot line. That means this is the movement of the base, Then because of the soil condition, building is rocking. So there is some displacement due to rocking also. And then deformation of the building itself. So total deformation is UT is equal to UG, ground displacement of ground plus displacement of the base of the structure plus displacement due to rocking of the structure. This is height into theta, sir. Height into theta, that is rocking. And then finally the deformation of the structure. But if we don't consider this soil condition, then what we generally use is the final U only. Only final U. That is the problem. The rest all three things we are ignoring. But nature will, when the ground is shaking, it will not ignore. It will be actual displacement. That means total displacement is the actual displacement. Now, we model, how to do? We model using spring. Here I am using only vertical spring, but there are two additional springs. One is horizontal spring as well as rotation springs. Two additional springs. Total 3 springs will be there in modeling this one. Now, let me show you one case study where we have considered 3 structures, a low-rise, mid-rise and high-rise structure, 5-story, 10-story and 20-story under 3 conditions, hard soil, medium soil and soft soil. So you can see here, the 5-story, 10-story, I'm not discussing much. You can, anyway, let's look at that. 5-story, this is natural period, change in natural period. IS code using the empirical expression, we get say on hard soil, 0.57. When it is fixed base, it is fixed base analysis, dynamic analysis or modal analysis, we get 0.64. Flexible base also 0.64. Not much change here. You can see 5-story building. Okay. But when it comes to even if it is 5-story building, when we are in soft soil, elongation of natural period is taking place here. 10-story building, further elongation is taking place. Now coming to tall building, which is the case right now. So 0.64 fixed 2 is the natural period using IS code method, means empirical expression. If it is fixed base, 2.28 seconds is the natural period. When it is on flexible base, it is 3.94 seconds. That means when we are using the soil springs, depending on the soil property, so period is elongating. And now we look at the base shear, which is computed against these numbers, above numbers. If it is hard soil, fixed base, flexible base, not much difference. But when it comes to soft soil, fixed base analysis is giving 371 kilonewton and flexible base analysis is giving 214 kilonewton. So that means it is huge difference. So we need to consider flexible base and understand understand it rationally, that what kind of forces are going onto our, coming onto our structure, what kind of forces are applied on the structure. Now, coming to another pile supported structure. In this one, when we did dynamic analysis, you can see the 2 time histories here. Fixed base analysis time history and soil foundation structure interaction based analysis time history. So blue color is considering soil structure interaction analysis, and green one is fixed base analysis structure. So green one is having a lesser acceleration, and blue one is a higher acceleration. You can see values are much higher if you are considering soil foundation structure interaction. And the same thing converted into frequency domain, we will understand it clearly. Here you can see values are, so Fourier amplitude spectrum, if we look at for the same values of time history, then here 20 amplitude, which is indicating at using fixed base analysis, is suddenly increasing to around 46 or 47 when we are going for soil foundation structure interaction analysis. Okay, so now how a structural engineer need to see when we are, say, putting a shear wall in the building. Why we put shear wall in the building? Because to attract larger amount of shear force, thereby moment resisting frame or moment frames will attract less shear force. So one typical case I am showing you some example here in this building at one diaphragm level. So which is at say 30 meters level. These are just representative what you call frames and shear walls. So here say frame is having say 10K stiffness. Shear wall, it is taking higher, it has higher stiffness, that is 35K, and here 35K and 10K. That means together shear walls are accounting for 70% of the total lateral load which is applied at that location, 70%, and remaining is going on to the frames, okay, moment frames. Now, if say for shear walls, like we need to design separate foundation because huge amount of shear force is transferred, and that is like at the base, if we see, it will resist by a huge moment. So like whatever force W or 100 kilonewton acting at 30 meters height, that means that horizontal force multiplied by the lever arm, it will be huge moment. So for resisting that, otherwise the edges of the shear wall will get crushed. For resisting that, we need to have a separate foundation for the shear wall. Now, if we don't account for soil structure interaction, then what is going to happen? Let me demonstrate it. Say modes of deformation. There are two modes of deformation. So one is the shear mode of deformation, and second one is flexure mode or bending mode of deformation. And there is a third mode of deformation when the soil deposit is not founded, when the structure is not founded on the hard soil. That is rocking mode of deformation. So this is a shear wall of height 30 meters height, and then 6 meters length with boundary elements also present. Then you can see, and then this foundation, separate foundation or special foundation is there, 4 meters and 8 meters, 4 meters by 8 meters, or 8 meters by 4 meters. So grade of concrete used is M50, and then W kilonewton load is applied at the top. And this footing is resting on the soil, which has a subgrade reaction, okay, of that value, so 30,000 kilonewton per meter square. And now let's look at the deformation modes in that. So shear deformation, let us look at shear deformation. So actually this deformation type depends on the aspect ratio. For this aspect ratio, predominantly bending deformation will be there, but let me explain you the shear deformation also. So this is shear mode of deformation, delta S. How do we compute that? So WH by K dash K prime AG. So K prime is shape factor, A is the area, that is shear area, G is shear modulus. So shape factor, I'm taking it as 0.8. Then area is computed for the dimensions. So 1260 into 10 power 3 millimeters square. And then modulus of velocity is also computed. So using these numbers, we get delta S. That means shear deformation at the top. That is 2 into 0.02 in 10 raised to the power of minus 6 W millimeters. Whatever load W is there, so W millimeter. This is shear deformation. And then shear stiffness is actually inverse of that. We get, so 49,000. So no, 49,4950. That means 495 10 power 3 kilonewton per meter. This is shear stiffness. Then second mode of deformation is flexure deformation. In this case, flexure deformation will be dominant compared to shear deformation. So flexure deformation, we know the formula. This is single curvature, not the double curvature. This is single curvature deformation. If it is fixed, then it is double curvature. Usually shear deformation comes under double curvature. So WH cube by 3EI, you know that. I we can compute using the numbers there. Already dimensions are available. I we can compute. So bending deformation is 6.24 into 10 raised to the power of minus 5 W millimeter. Here you can see bending stiffness. So bending stiffness is lesser than shear stiffness. If you can see, remember the earlier slide. Okay, one order less than the earlier one. Then the third one, this is rocking. So shear deformation, bending deformation are easy to compute, but the rocking deformation. Rocking deformation is what? Because of the soil underneath the structure, that means underneath the foundation of the structure. So this is rocking deformation. So whatever is the theta, we can compute that theta. I'm not going into those mathematics. What is delta R? Delta R is that rocking rotation multiplied by height. So that is rocking deformation. So I'm just expanding the base. So the foundation is resting on springs, that is soil which is modeled as springs with the given subgrade reaction. Now when building rocks, when structure rocks, what happens is like this. So from center at a distance of x, right? So subgrade reaction, what is subgrade reaction? So that's some like reaction per millimeter of what do you call, deformation of the foundation inside the soil. So that delta x is the deformation. So now this is the foundation. In that strip, if we compute the force, so what will be the force? That force will be like K is the modulus of subgrade reaction, B is the width of the footing, that is 4 meters, and at x distance, x theta. So x theta is the deformation of the foundation, and then multiply by the x. And if you completely integrate, then we get the moment. That plus 4 to minus 4, that means 8 meter width of the length of the foundation is there. Length of the foundation is 8 meter, width of the foundation is 4 meter. So if we compute this one, we get moment. Integrate it, compute it. I'm not going into that mathematical expression. So moment. Now what is that moment? It has to resist, it has to be equal to the moment which is coming from the top. The top means because of the lateral force, that is W multiplied by H. So W multiplied by H. If we equate these two, we get theta from that. Okay, so if I plug in the numbers, what I'm getting is 9.325 10 power minus 7. W is the rotation, that means radians. Now using that, we get the rocking deformation. This is 2.81 10 power minus 5, and then rocking stiffness or rotation stiffness. So that is 35587. Now we have three deformations: delta shear, delta flexure, delta rocking. Three deformations. Shear mode, flexure mode. Oh, sorry, it's reverse. Reverse names are reverse. Okay. First one is flexure mode. Second one is shear mode, and then third one is rocking mode. Just numbers, names are different, interchanged. So Ks, we have this number: stiffness, bending stiffness, and then rocking stiffness. Now, if you see the numbers, okay, so which one has higher stiffness value? Shear deformation. But anyway, in this case, bending deformation is dominating. So we take bending deformation along with the rocking deformation. That means total delta, that is total deformation, is the addition of bending deformation plus shear deformation. If I add up, then I get the total deformation. From that total deformation, if I compute, I get this is a shear, what do you call, stiffness of the shear wall, stiffness offered by shear wall. So now here, earlier stiffness offered by shear wall, if I look at it, sorry, this bending deformation 16025 is the one which I take into account. But actually what it is offering is 11. That means I am accounting for 50% more stiffness. That means what 50% more stiffness means. Now in this case, I am under the assumption that 70% of force is resisted by shear wall, but actually 70 divided by 1.5, that means 1.5. Only that much will be taken by the shear wall if we are not accounting for soil structure interaction effects. So that means what, if 100 kilonewton load is applied, our assumption was that 70%, that means 70 kilonewton is taken by shear wall, but 70 by 1.5, just one second, let me compute and tell. 70 divided by 70 divided by 1.5. It is taking only 66. That means extra, that lateral load will go on to moment frames which are not designed to take that kind of load. So this is all. So there are four, like these are, if you are not accounting for soil structural interaction issues in the design of tall buildings, then we will be in problem. So this is my last slide. Let me go to the summary of my presentation. So we are discussing about tall building safety with respect to several geotech issues. So macro seismic hazard values will not work for tall buildings. We need to go for site specific hazard assessment. And then IS 1893 gives a flexibility to increase the bearing pressure of soil, that also we discussed. And then liquefaction potential assessment step-by-step procedure given in 1893 we discussed with an example problem. And then lastly we discussed soil structure interaction assessment also with two examples. One is like manual calculation we can do, and then computer-based analysis we can do. So in summary, we need to follow stipulated code provisions and understand this is for the safety of the structures, whatever structure, either low-rise, mid-rise or high-rise building. So with this, I would like to stop here, and I thank IS 30 for giving me this opportunity to present whatever I know on this subject matter. And then I sincerely thank all my research students, which I have presented. Actually, the work of those students I have presented here. And then again, thanks to internet for all the many images which I have taken. So thank you very much. These are my contact details. Sir, over to you, Tandon sir.
Thank you, Professor Pradeep Kumar. That was wonderful. It was very well illustrated. I am sure that your students must have made all those sketches because we have less and less time to make sketches, and we are not as efficient as we used to be. But the youngsters are very good at that. So Professor Pradeep Kumar has concentrated on three issues which relate to tall buildings. One is that just using the map suggested accelerations and designing a tall building is not adequate. You have to do a site-specific hazard study in order to be able to do the tall building. That's the first thing that he has mentioned. The second thing, of course, he went into the soil liquefaction, more a sort of elaboration of what the IS 1893, I think it's Appendix F, if I remember correctly. Yes. That is where the methodology of evaluating soil liquefaction is given. And he has emphasized that you have to find out for every layer, you have to check whether the soil liquefies or not. You may have something which is liquefying at the top, and then nothing liquefies, and then again something liquefies when you go below. So every soil layer, depending on its characteristics, has to be checked for liquefaction when you are doing a liquefaction analysis. third thing he mentioned was about soil structure interaction. And soil structure interaction, why it is important for tall buildings. If we just consider the building as fixed at the base, it is not enough, because the building is not really fixed in space at the base. Firstly, the ground itself may shake, which means that the building may move, even the foundation may move in the direction in which the earthquake force acts. The other things are that you have a rocking motion. That means that the building doesn't remain the same in the same configuration. It is just not moved to another spot, but you can have a rocking motion also. And of course, the building itself may deflect, even if you fix it, even if you consider it fixed at the bottom. So it's a number of things you have to take account of when you are considering tall buildings subjected to earthquakes. The other things that he mentioned was about the map itself. And I would like to elaborate a little bit on it, because the map of IS 1893 is under revision, and we are very hopeful that after many years we will have a new map. At the moment, the map, some of the things that we have found, what is wrong with it is that if you move 10 kilometers from one place to another, you may suddenly change your the zone factor from, let us say, 0.24 to 0.36, which is 1.5 times. Now that can't happen in 10 kilometers. And there has to be a transition which we have to give in the map, which is also being considered at the moment, whether we should give contours or whether we should give the way it is. That means we consider zones only, the way that it is shown here. But then we have to solve the problem of the borders between the two zones. In engineering practice, we can accept a variation of 10%, 20%. That's all the accuracy that we aim for, but not 50%. Here, what is happening with the existing map is that you are getting a difference of 50%. And the code says, if you are in any doubt, use the higher value. Now, that is not the scientific way to go about it. So I hope that this will come. And the other thing is that our map only gives you acceleration. It doesn't even tell you that those accelerations are at the rock level, which is somewhere way down. It depends on where the rock is. And there is an increase or enhancement of the shaking when you come to the surface. If you have a soil layer above the rock, then it is increased. And that part is not covered in our code, which is, I hope that the new code, which is under development, and we are having frequent meetings in that it will cover that also. The other thing is that even when you are finding out the liquefaction, whatever is mentioned, they have mentioned a factor called MW, which is the moment magnitude of the earthquake, without defining where do you get this information from. Magnitude of earthquake at a particular place, you have to define where it comes from. And of course, there is another code which is under preparation by the IRC, in which we are trying to define how to relate it to whatever information we have. If, for example, you have only the information regarding acceleration, then what is it likely to be? What is the magnitude of earthquake which you should consider for the purpose of liquefaction? at that particular spot. So these are some of the issues which some things we know, something we don't know, and there is no, apart from saying it's a design basis earthquake, we don't know whether it is, what is the probability of its occurrence, what is the frequency of its occurrence. Nothing is really given in the code. And of course, it's a work in progress. But now, finally, I think we may find in the new code all these issues will be addressed. So, looking at the questions, we have a few minutes. So we will, if I can just see some of the questions. I don't know whether in the meantime, Professor Pradeep Kumar has seen and if he wants to answer anything, or should I just?
I've seen, sir. Yeah.
Sorry?
There are many, one second, sir, I'm seeing. I could see the question. There are many things like appreciation kind of comments are there. So, but besides that, one question is, yeah, is there ideal fixed base criteria in any code? So, no, that is only for our understanding. Like as I told you, like low-rise structures, mid-rise structure, high-rise structure in that matrix. If it is mid-rise structure and low-rise structure in hard soil and medium soil, then we may ignore it. But for rest all the cases, soil structure interaction is compulsory. So it is better we need to learn. Okay. So please tell about rocking shallow foundation. So it depends on that modulus of subgrade reaction when we compute it. Then with this spring constant, we will know what is the rocking theta value. So with that theta value, we can get, say, deflection. If the deflection is large enough such that it is reducing the stiffness, the overall stiffness, then we may take that also into account while fixing the lateral load, like shearing capacity of that structural element. Okay. One second. Somebody wrote, how can we increase the N value if it is deeper? Okay, so deeper level, right? Yeah, somebody wrote, it's not 66, 46. But yeah, I also realized 0.5 is that value. Thank you for pointing it out. So yeah, so 70% of the 70 value actually, I told 66%. So value is 46.67 kilonewton will be taken, but remaining will go to moment frames. So how to increase N values when we encounter it at the greater depth? So there are soil stabilization techniques are available, which my suggestion is you consult a proper geotechnical engineer. What I've given is the structural engineer's perspective and what we need to know as a structural engineer. And also, this is actually amount of money which we need to spend may be high, but compared to the overall structure cost, it is not that much. So please start investing in geotechnical explorations. Otherwise, what will happen is what Tandal sir has presented at the beginning. We should not go into such kind of scene.
I think there are some questions in question answer block.
Yes, sir, I'm not able to see.
There's a lot of comments here and there.
Yeah. There's some question from Amit Patel.
Dynamic stiffness and
when we need to account for dynamic stiffness and damping of soil. No, all the time, actually, all the time we need to account for dynamic stiffness and damping. Actually, it is linked with the damping value. So in like cyclic motion, every hysteresis will reduce the stiffness, and damping value can be calculated using that hysteresis cycles. Actually, I've wanted to put that, but I thought it will be like too much on the presentation slides, so I've removed that. And second. Yeah, another question is by Mr. Baban Kumar. How can we model the rocking motion? So rocking motion can be modeled by giving rotation springs. So 2 translational springs and 1 rotational spring. So vertical spring, horizontal spring, and rotation spring. 3 things. Okay, what can be the remedial measure if the well foundation of major bridge settled and tilted due to reduction in embedment depth because of plundering of bedrocks with raker piles work to reduce further settlement? This is a situation near Haridwar. No, sir, I am not expert in that. I will not be able to answer that question. Maybe Tanan sir can.
Can you just tell me where it is? Is it in the chat or is it?
In
are you
the
looking?
chat, sir, in the chat. In the chat.
What is the question?
This is, I think, from the bottom, third question. What can be the remedial measures if well foundation of major bridge settled and tilted due to reduction in embedment depth?
Cause of plundering
Yes.
of bedrocks.
Yes.
The raker piles work to reduce further settlement and tilting. This is the situation near Haridwar. You see, the India is a country which has the maximum amount of experience in well foundations. For generations, we have been, that is the only type of foundation which we have been using for bridges across rivers. So we, whenever we have up to, let us say about 15, 20 years ago, we were sinking the wells by their own weight. And that is why we kept a large steening thickness in order that the well can go down. As you know, to send the well down to the base where you have the founding level, you have to excavate all the soil inside the well so that the friction there reduces and you have friction only on the outer surface. So that is how we have been sinking well. But obviously, when you do sinking like that, there is a chance that you may encounter different types of strata on one side as compared to the other, and you may start getting tilt. You may also the well may not be exactly at the same place. Of course, there is no earthquake here, but it's like the what Professor Pradeep Kumar mentioned, that the building doesn't remain at the same place. Similarly, if you have a well foundation which you are just sinking by its own weight into soil, it may not remain exactly vertical. That vertical axis itself may shift if you get different types of strata. So how to rectify these tilts and shifts? We have a large number of case studies, and you have to study them. Almost all of them are available in various papers of Indian Roads Congress. If you see the number of papers that have been written on the subject is amazing, and different types of remedial measures have been taken in different projects. But in the last 20 years, we have something else, which means that we don't depend only on the self-weight of the well to go down. We have something called the jack-down method. Jack-down method means that you put some steel grillage at the top of the well and apply hydraulic forces by hydraulic jacks on it. I mean, there is a system of doing it. So, and then you can adjust. Let us say that there are 4 jacks that you are using to force the well to go down into the ground. So by adjusting the forces in the 4 wells, if you know the techniques, you can correct to a large extent the tilt and shift that you otherwise may have. And the idea is to use these jacks and differential pressures in the jacks from the beginning. Once you have a problem in the of shift or tilt, and you don't pay attention to it, catch it soon enough, then you are going to get into bigger and bigger trouble. So, I mean, for example, in the old days, we used to put the load on the side, which is, if the well has tilted, you put the load on the other side, much like what the San Francisco fellows have done. They are trying to put piles there. Instead of piles, we put load on top where it is, where we want it to go down. So it's something similar which you have to do by means of rectification. And like I said, there are many case studies which are available as to how to do it. So what are the any other question which
Yes, sir, yes, sir. There are some questions in question answer this one section. So which like I will take some of them, and some of them I'll answer it separately because these are available anyway. Okay, so I'll take purely geotechnical. I'm not touching, but structural engineering and geotechnical I'll address first. So deformation from shear, bending, and rocking have been added. So is it okay considering that during earthquake, building may have geometric nonlinearity, soil might not deform uniformly? Yes, there is a possibility. There is a possibility of geometric nonlinearity maybe occurring first, then this kind of thing. But we can add whatever is the predominant deformation, that is bending and rocking. So these also will get added. But which one will start first? It depends on the type of ground motion which is which building is experiencing. Okay. So the speed delta analysis, which I have explained in the last session, if we consider, we will understand it. Okay. So which one will be predominant? Which one will occur at the beginning? So whichever is occurring at the beginning, and like later also, if other effect also is SSI gets added, then there will be a problem.
If I may just add here,
yes, sir.
Since we are talking about the soil, see, most of the softwares which are available today, we are, that we are going to model the soil as springs. For example, if you have a pile which is surrounded by soil and it is subjected to horizontal forces, you model the soil as springs. Now the question is, how do those springs work in an earthquake? One thing is that you say that it is just a spring and it remains elastic all the time, and whatever is the deformation, that gives you the force. But in actual fact, we know that the soil will not behave like that. It may go into non-linearity, and it will almost certainly will. So there you have two choices. The simplest choice, which is available in all, well, not all, but most softwares, is that the spring is treated as a bilinear spring, which means that it goes elastic up to some stage, and then it becomes becomes horizontal. That means that it cannot increase beyond that. That is a idealized diagram that you have for the soil behavior when it is goes into the nonlinear state. Of course, you also have the possibility of idealizing the soil in the actual curve that it behaves. But for simplicity in all structural engineering applications, we try to do a bilinear spring so that it is easy to understand it and you can finish the problem quickly. And how to do this, of course, it is given in a number of books, but we are also going to have a publication soon in the Indian Roads Congress, where we will explain how, depending on the type of soil, how you can, how to idealize it. As to first is to find out that point at which it no longer behaves like a linear uh, material, but it becomes plastic beyond that point. So how to find out that point and what is the value of this plastic, the ordinate of that, all that will be given. So it's something which is you can use.
Yes, sir. Some of the answers I've typed here, and yeah, the question, yeah, Santosh Babu, how can we ensure gravity columns in dual system in ETABS? No, I'm not discussing that here. The software, the general principle behind this SSI liquefaction potential assessment, which a structural engineer need to know. So those things are discussed. Yeah, in pile cap and pile foundation for tall building, as per table 1 IS 1893, can I take benefit of increase of pile vertical and lateral capacities in earthquake case? Yes, yes, we can take advantage of that. Yes, Amit Patel, we can take advantage of that. But the only thing is, if there are liquefiable layers in between, we cannot consider those layers in the analysis. So that, yes, you can take advantage of that. And done. There's a question by Sushil Dhawan. Soil structure interaction in tall buildings in different soils. That's all. Nothing. I think question is incomplete. So I don't know what to do.
I think that's what this whole lecture was about.
Yeah, title of the lecture. Yes. And there are some questions related to specific projects, name like Narmada Bridge team of L&T, all that kind of things are there, which I'm just not taking it up.
So I think that we should,
yeah.
If you want, you can take the last question or something like that, so that we can.
Just 1 second, sir. Let me look at in the chat. How to combine total lateral seismic load on piles due to superstructure and foundation? If the superstructure is flexible and foundation is relatively stiff, and they usually respond out of phase. How to combine total lateral seismic load on piles due to superstructure and foundation? No, I didn't quite understand the question.
So I think since we are coming to the end of our time, and our president, Mr. Manoj Mittal, is also seen on the screen. So may I request him to say a few words of advice for all the participants?
1 second, sir. If participants feel that their questions are not answered, you can send it to be my email address. So I'll answer them leisurely, okay, with some more additional information. Okay. Thank you.
Thank you, Mr. Pradeep Kumar. So I think the participants should be happy in case we have missed out in answering any question or not answered it well enough. You are most welcome to write to Professor Pradeep Kumar, and I think the email address is given. It was shown in the beginning. We can show it again. And so that's an additional benefit that we can provide. So, Mr. Mittal, your turn.
No, I have nothing much to say. Only thing is, I really enjoyed your lecture, Professor Pradeep Kumar. I actually missed the initial part. I was out of office actually, but I really enjoyed your presentation. I think you are a very good teacher. I think your students will be very happy at IIIT. Your lectures are really very good. You explain the things in a very simple language, and it's really very interesting and nice to hear you always. So we are very lucky that we have 2 more lectures from you in this series. And another important thing is that you have started the monthly lecture series in South in association with IIIT Hyderabad. So the first lecture which was there of Arun Menon from IIT Madras, it was really a fantastic lecture. And I hope all the lectures every month which you are going to arrange, manage, I think they will also be very interesting, and I will definitely be joining all the lectures. So thank you, Dr. Pradeep, for excellent presentation, and Professor Tandon, you are a very excellent moderator and speaker, and you are excellent actually in every all respects, in all respects.
Thank you.
And,
Thank you.
and I also want to thank all the participants who joined the webinar. And I just wanted to again emphasize that all participants, those who are not the member of IS Structi, they should definitely join the IS Structi, since IS Structi is really doing very good, fantastic job. We are arranging so many technical events, and we are publishing so many guidelines and code commentaries, and we are doing so many things. So as such, ISTEC is a very active, cohesive, and vibrant body, and I would like all of you to become active part of this association. So if you are not a member, please try to become the member. If you have any difficulty in becoming the member, of getting the form or getting it supporter or anything, you can contact our secretariat, or you can contact our office bearers. If you are in South, Dr. Pradeep Kumar is our vice president. You can contact him also. You can contact any office bearer. We will help you to become the member. And once you become the member, you will see that you will be much more involved actually, and you will feel much more satisfied rather than just participating in the events. So this is my suggestion, request, advice. And again, thank you everyone for joining.
Okay.
I say one last thing.
Thank you, Mr. Mittal.
Next lecture will be,
yes.
Sir, next lecture will be on disaster risk indexing of cities. So in that, I would like to present at a large scale, how do we rank cities, and a group of buildings, how do we rank them. This is very important from the disaster mitigation point of view. So that is the next lecture.
And another important thing is, tomorrow we are starting a refresher course on structural strengthening and rehabilitation. And the faculty there is excellent. We have very good faculty and course structure which we have developed. It is a very unique, and I'm sure those who will be attending, they will learn a lot about this field. And I'm sure the future of the structure strengthening, rehabilitation, and retrofitting is, I think, future of the structural engineering. This area will grow actually in time with time. So I think it's the right time to learn about all these things. So those who have not attending, they can also think of attending it. It's still there's a time to register, and you can go through the. I'm sure everybody must have got the information about it. If it's not there, then you can contact the ISTT secretariat, and we will give you all the information. You can join the course also.
Okay, so just to summarize what has been said in the last few minutes, actually every after fortnight, the next lecture in this series which you are attending today, the next one will be after a fortnight, and the last lecture will be a fortnight after that. And these are on Fridays.
Yes.
The the structural engineering retrofitting course that Mr. Mittal talked about is on Saturdays, and it is on every Saturday. There is no break.
Yes.
So
it will end on 2nd October. It will continue till 2nd October.
It will continue till 2nd, starting tomorrow up to 2nd October. So keep your calendar updated. The one about this series which we are listening to, that will happen after 2 weeks, and then again after 2 weeks. And the structural rehabilitation, that will start tomorrow. That's the first Saturday. And then it will keep on happening every Saturday right up to 2nd October.
And sir, there's one more information. This time in this fresher course, apart from the participation certificate, we have introduced the concept of issuing the proficiency certificate. It means after every lecture, there will be some kind of assessment and those who will attain a particular mark, they will be awarded proficiency certificate also, in addition to the participation certificate. But this certificate will be on voluntary basis, not mandatory. Anybody who wants to get this certificate, then they can appear for this assessment. So this time in this course, we are starting that thing.
Yeah, I think that there was a big demand that it is very easy to get a participation certificate, but how do we know how much the person has actually gained from it? And there are many people who want, some kind of a gradation of that. So the idea is that after every lecture, is that right, Mr.
Yes,
Mittal?
sir. Yes, sir. Yes, sir.
After every lecture, whoever wants, it is all voluntary. If you want a proficiency certificate, you have to appear in that, very short and very simple kind of a test. And if you, depending on your performance there, you would get a proficiency certificate in addition to the participation certificate, which you will get in any case if you have joined the.
If you have attended 80% classes.
Yes. 80% classes are 80% lectures you must attend in any case before you can get the participation certificate, and that will be at the end of the course.
Yes.
Both these will happen at the end of the course, but this is just to inform you. Okay, then I think that we have more or less finished our agenda today.
Yes, sir.
And after this wonderful presentation that Professor Pradeep Kumar made, I hope that you have got something to think about and become better engineers. I certainly will become a better engineer as a result of the things one has learned in this short period of 1 hour that Professor Pradeep Kumar gave his lecture on. Okay, with this, I think we will close the session. Yes, and see you tomorrow.
Yes.
And see you after 2 weeks for the Professor Pradeep Kumar's third lecture.